This is random stuff, but it's a lot of it's like educational stuff. Okay, got my video going. Yay! All right, guys. This is the last content that I got covered for the class. Yo!
Mr. Hall,
What?
we should play a game after you're done with me.
What game?
It's a fun game.
A trivia
Celebrate.
reboot.
Yeah, to celebrate the end of material.
The game is done. You have to play.
I have play Hall.
Yeah.
I would totally do that. I can.
Do you know how to play? Do you know how to play? Okay. Okay, so when I'm done with this, if you guys want to go over an example or two more of like, say, the envelope functions or whatever, that we can do that, or the reciprocal functions. But today we got to do inverse sine, inverse cosine, and inverse tangent. So let's do inverse sine first. Luckily, we have already kind of covered this.
Yes.
When we were just,
Hello.
let's do a little refresher over here in the corner. Does anyone think they know what is the inverse sine of 1/2? Just a little trivia, not trivia really, but just a little warm-up question to get us started. Who's feeling confident? Anyone?
Yeah.
5 or 6. Very good. Sorry if you said that. I couldn't hear you, Alyssa. But.
You know when you like say something in class but you're not sure if it's right, so you do it really quiet.
Yeah.
Someone else says it louder and they get credit.
Yeah. I know exactly what you're talking about. Yes.
Would it also be 5 pi over 6? Would that work too, or am I?
You are very
no,
much
no.
on point as far as
I remember now. You stay in the one spot. Yeah. I forgot.
you guys already said that it's a good thing to know of. So like if you say sine of what, if you say sine of what equals 1/2, there's an infinite number of answers to that question. One of them is 5 pi over 6. One of them is 13 pi over 6. No, sorry. Yeah, 13 pi over 6. And so on. But this, like, we limit the domain of the function. So, and then why is this true? This is true because the sine of pi over 6 is 1/2. Okay? Because that's, remember the whole inverse function thing? Swappy. So, watch, it's actually not going to be, it's going to be pretty painless. So let's look at the sine function. The sine function looks like this. The way I'm drawing this, does this guy have an inverse the way I've drawn him?
Yes.
No.
Oh no.
He fails the horizontal line test. So what you do is you pull a little bit of a trick and you say, well, I'm just going to select a part of this function that kind of covers the whole range of the function, but never repeats a y value. So see if you can visualize what chunk of the function does that. There's actually a bunch you could pick, but this is the best. This is what. What? What's so funny?
So it's one for Chromebooks
You, Mr. Hall.
Me?
Lying at you.
and one for chargers.
Oh, thank you.
That makes sense?
Yep.
Memester.
LOL.
What? What did I do?
Lol. You'll never know.
Okay. This is the part of the function we're going to isolate. So that's the part we're going to invert. And so what that ends up looking like is this. I forgot to do one important thing. Sorry. Let's identify the endpoints of this thing. So like, there's 3 points that are really relevant. This guy, what's his x value? His x value is I over 2. His y value is 1. So if this point lives on this graph, the one we want to graph, the inverse function, what point has to live on him?
1 pi over 2.
1 pi over 2. So I'm going to graph the point 1 pi over 2. So good. Is everyone still okay with that general concept of inverse functions and how, like, if the point 2,7 lives on f, then the point 7,2 lives on f inverse?
Yeah.
Okay. Great. Similarly, this point is at negative pi over 2, -1, so therefore my other graph is going to contain the point -1, -pi/2. And of course, 0, 0 becomes 0, 0. Probably the trickiest part of this is getting the curvature right, although that's not really. You see how that's kind of like if you reflect it over the line y equals x, it would invert the curvature. If I curved it the other way, it would just look like a sine function again, so you didn't really reflect it. So anyway. We could consult Mr. Desmos and say, "Oh, great machine! I beseech thee, give me your knowledge." I'm just going to type in mark sign, because that's the same thing.
Whoa.
So the other class, some people had some. I mean, the comment was like, "Wait, is that it? Like, are we done, or is that just one piece of it?" No, that's it. That's the whole function.
Oh my god.
Because that's the only way you can keep the function invertible. If you keep going, you'd be repeating stuff, and then it would no longer be invertible. So,
Well, you can make like a flower if you keep doing that, but just like tilting it to the other way.
Rotation.
another flower,
Yeah.
If you rotate.
like shift it.
Like 40, rotate it 45 degrees.
We gotta rotate it.
Yeah.
I can do this.
Ooh.
It's kind of neat.
That's a double heel.
It's a man getting ready to dive into a pool. Or like
I
he
know.
is in the
What?
process of diving.
I don't see.
Yeah.
What?
The other
His head is
class
right there and he's
said that
falling.
it looks like toothpaste.
I think
I don't
mine's
see the
better.
toothpaste personally, but.
I think mine's better.
This is
Okay.
like constellations.
So, when the non-seniors, when you take your last quiz, well, I almost said juniors, but I would be leaving out these fine sophomores up here.
I'm so cool.
You are so cool. I agree. A question you might be asked is just, hey, there's an inverse sine function. What's the coordinates of like this endpoint here? That's a question you might be asked. Okay. So, what happens if you can you stretch these guys and shift them and all that stuff? Yeah, they're functions. They behave exactly like every other function. So if you, for example, put a 2 in front of it, it's going to stretch it vertically by a factor of 2. If you throw a 2 next to the x, that's going to crunch it horizontally by a factor of 2.
So for like the cosine one, since like the sine function is just the cosine function moved over half pi, would that be the same for inverse cosine?
Moved up.
Sort of. Inverse functions are tricky though. Like for example, take like a square root function and shift it to the right, and then invert it. Because shifting shifting a square root function to the right and then inverting it, well, the inverted function is shifted up. So I guess what I'm trying to say is it's not quite as direct as being like, oh, it's just going to be a shift of pi over 2. That's a good point. I like where your mind is. It's a good idea.
Like where your mind is. It's in a good place.
It is. Okay, let's do inverse cosine next. The cosine graph looks something like this. You once again go, wait a second, you failed the horizontal line test. So we have to just isolate one part of you that never repeats a y value and also hits every y value. Hopefully we see it. You got to go from here to here. What was that noise for?
I'm writing in pen and I messed up my cosine graph bigly.
Bigly.
Do you have a erasable pen?
Okay, so it's this part right here. Notice the graph goes from 1 to -1. Okay. Why do they not pick this range? I don't know. You certainly could, but then all your values are negative, so maybe it's not quite as nice. So in this case, look at how all of our x values are positive. See that? between here and here, all of our x values are positive. So on our inverse, all of our y values will be positive. That's kind of nice. Inverse cosine. This is a nice marker. Okay, this point right here, let's just list them out real quick. This point is coordinates of 0, 1. This point down here is coordinates of pi, -1. And this point here has coordinates of half a pi, 0. So let's put all those points on our inverse. Well, swapped versions. 0, 1 becomes 1, 0. Pi -1 becomes -1 pi. Pi's kind of up here. Is this making sense? Yeah, so we've got this point. So 0, 1 becomes 1, 0. Pi -1 becomes -1 pi. And then pi over 2, 0 becomes 0 pi over 2. And so for the curvature, once again, kind of a tricky part getting the curvature exactly right, but it looks something like that. Oh, great machine. By the way, Desmos does have a thing where you can, if I click this keyboard, hit functions, I can get the inverse cosine like that as well. What's wrong?
That's cool.
Yeah, I think it's a neat function. We should also do cool stuff like, I don't know, what happens if you did like, I don't know, the reciprocal?
Cannot draw.
What does that look like?
Well,
It's kind of a weird function.
why do that?
Well, why does it look like that? Because
Erase it.
as x approaches 1, inverse cosine approaches 0, so therefore the reciprocal of inverse cosine would be just eating up to it. Okay. How do we feel? Did you lose yours or did I not give you one?
I have one. I think I forgot it.
That's okay. No worries. What, Taylor?
Nothing else.
Where's my rubber bands?
Mr. Hall.
I need to.
How do you shoot rubber bands? I can definitely figure it out.
I'll teach you when we're done here.
That's funny.
All right, last one. I'm sure there's no questions? You sure? Okay. Let me throw out a quick a little example. Just let me throw it out there. What would happen if I wanted to graph like y equals the inverse cosine of x over 2? Is that like a very long, taxing process?
No.
No, it's actually fairly easy. All it's going to do is double all the x values. So now, instead of 1, 0, it would be 2, 0, and -2 pi. Yeah, the y values wouldn't be affected, and you'd have some shape kind of like that.
Oh.
It's kind of exaggerated, but
So,
yeah.
If like the numbers in the parentheses, then it's then it affects the x value both it's in front of the like in front of like the cosine or like whatever, it affects the y value.
Totally correct, yes.
Aha!
So as you can see, as I make this a value bigger, just kind of notice the y values, like the range doesn't change. I'm just changing the x values. I can throw a number out front here. I can throw like a c out there. Now I can stretch vertically as well.
Whoa, it just stays on at one point.
Okay. Anyway, get the idea? Yeah. All right. So, like always, guys, if you're confused at all about any of these functions, it's nice to have this like free technology that you can. If you spend 10 minutes playing around with that, I think it's going to click for you. Kind of like, oh, how do these values? How do you shift this thing? How do you stretch it? Okay. So, last one. This last function is very interesting. It's very useful in proving. Well, one of the proofs it's for is to prove that there's the same amount of numbers between 0 and 1 as there are between 0 and infinity, or negative infinity to infinity. Kind of neato burrito. Because it maps an infinite number of numbers down into a small set of numbers, or into a bounded set of numbers. Okay, the moment you've all been waiting for, the tangent, the inverse tangent. Now this guy, we know what he looks like, hopefully. What part of him are we going to select?
Middle.
Probably
Just
the middle notch.
Yep. The middle one. Seems like a pretty clear choice,
Yeah.
right? Because here's the tangent function.
Oh man, but there's only one solid point we can identify, and then the rest are asymptotes. Whatever shall we do?
Well, we're going to isolate this
Try.
part and say that's the part we're going to invert. And so the inverse
No.
tangent function.
It's a little.
Well, I mean, I get what you're saying, but if you really wanted to go point by point, you could say things
Easy
like
point to identify, Paul. Easy point.
how about pi over 4.
Okay, I didn't think of that one.
1. That's pretty easy. Right? Or pi over 3 gets you root 3. But we're not going to have to do that because remember that whole thing about how so if a function f has a certain domain, what do you know about the inverse? Well, the inverse's range is the domain of the original dude. Remember that, the swapping of the domain and range?
Yes.
Or no?
Yes.
So if we're just focusing on this thing, what's the domain here? This.
Yeah.
The domain here, the x values are numbers between negative pi over 2 and pi over 2. So therefore, this guy is going to have that as his range. So this guy has vertical asymptotes. His inverse must have horizontal asymptotes at pi over 2 and negative pi over 2. Okay? Feel okay about that?
Yes.
And then, 0, 0 is on tangent, so the same point must live in the inverse, and curve looks like that. So it's one of those interesting functions where the domain is all real numbers, and the range is just this bounded set of numbers that's only about 3.14 units tall. And then, get it. I mean, the intuition here, I hope makes sense. It's kind of like on here. As your angle gets really close to 90 degrees, your tangent gets really, really, really big. So conversely, or inversely, as your inverse tangent value, or as your x value gets really big, the inverse tangent approaches 90 degrees. Pi over 2 radians. Key. Doki.
Okey-dokey.
There's one more. A rough time with drawing that curve, didn't you?
You can't draw a curve.
Dude, I knew so many people in college that were way beyond my skill levels of that, but they couldn't draw like this, and they couldn't draw this.
It takes
It's
some
really-
brain power.
Wait,
That
what?
top one's a little hard.
I know I
to
can't.
For
I can do the upper to do the top.
Remember piecewise functions?
Yeah, but that one's hard to draw.
I'm not saying it's easy,
Others
but
are like,
You do it so fast, too. It's so smooth.
impressive.
It's very
It just
good.
requires a little thought.
I don't take it math though. That seems like it would be needed, but I don't.
it's like the one thing I could do better.
You got perfect circles.
No,
Oh.
You gotta go in.
I can draw an okay circle.
Let's see it.
You've seen me draw a million circles.
Yeah, try really hard to make it perfect.
There you go. That's my best effort.
Ooh, that's pretty good.
Okay, so guys, the very last page is it's a bit of an afterthought here, but I hope we can get something out of these. Okay, last page. It's going to ask you questions like this. Now, it's not asking you what's the answer to this. It's just asking, is there an answer to this? And if there is, how many answers are there? How many solutions are there? You understand the spirit of the question? So is there a number or multiple numbers where the log base 2 of that number is equal to the sine of that number? Let's see. Let's try to figure one out. It's the last page. Oh, it's okay. So you take a graphical approach. For this one, you got to be a little precise because can anyone name me? Well, hold on first. Do we know what this looks like?
It's the dude.
I don't know why I asked these questions. Just setting myself up.
I'm kidding, Mr. Hall.
Okay. So it's that swoopty-doopty shape. There's an asymptote at 0. X equals 0. Now there's 2 critical points you got to know about on this graph. There's the point 1, 0, and there's the point 2, 1. How do we feel? We understand why those points both live on the graph?
Yeah. Because the log function intersects the x-axis at 1.
Well, these are 2 like fairly straightforward facts, right, about logs. Log base 2 of 1 is 0 because 2 to the 0 power is 1. So therefore, when x is 1, y is 0, right? And then log base 2 of 2 is 1 because 2 to the 1 power is 2. And therefore, when x is 2, y is 1. You feel okay about that?
Yeah.
Okay, now why am I so keen on those points? Well, the range of this function is -1 to 1. So it makes sense that I'd want to know where does this thing go above 1. Because once this guy's above 1, he can't possibly intersect this guy anymore, right? So this guy has 0, 0. And where's another point that's really relevant for this question that lives on him? Pi over 2, 1 is definitely 1. So here's the number. So here's 1, 2, 3. So where's this thing going to cross the x-axis? At pi, right? 3.14? And where does he reach his peak? Where AJ said, halfway between 0 and pi. So around half of pi is like almost 1.6. Is making any sense?
Yeah.
And then I don't really care about the rest a ton just because I know it's never going to go above this level of 1, right? That makes sense? So for the rest of his life, he never goes above 1. So how can he possibly touch this log function that has been increasing since this moment? Is this making sense?
Yeah.
Okay, so we know there is one solution, just for funsies, taking bets. What do you guys think x is going to be? I'll use a computer to solve it in a second.
1.666.
1.6? 7? Okay. It's a good guess. Could be 1 point.
1.2.
As usual, is it? I can check my answer. Log base 2 of x. It's actually 1.919. Okay, that's a little bit bigger than I thought it was going to be, but yeah. So, but you can confirm from the graph, right? There's only one solution. And look, we did a good job of ruling out any other possibilities. Okay. So the rest of the questions on that page are just like the same thing. You just say how many solutions are there and support your answer with a little graphy. Okay. Kahoot time? What do you mean?